So let's do a center of mass example. I'm going to start with three objects, and then I'm going to put them together and ask where the center of mass is. Actually, let me just do a real quick aside and say, let's say I have this mass m1 and m2, and then let's say m2 is twice m1. What is the center of mass? The center of mass is going to be, you can figure it out. It's going to be 1/3 of the way along, but you can at least you know that it's slightly closer to m2 than it is to m1, somewhat closer to m2 than it is to m1, because m2 is bigger than m1. So the center of mass, I draw a line, but the center of mass is a point, right? It's a point right there. The center of mass. That's the position of the center of mass. Hold on. So assuming that these two are lined up vertically, so that their centers of mass are on the same vertical line, then the center of mass is on the vertical line that connects the centers of these two objects, but it's 1/3 of the way closer to m2 than it is to m1, if m2 is equal to twice m1. So you can figure that out for yourself. But so the point is that this point right here is the position of the center of mass, whatever that position is. Okay, so these two objects have a center of mass even though they're not attached. The point that I want to make is if these two objects are floating in space, if they are the Earth and the Moon, which don't have this mass ratio, but if they're the Earth and the Moon, there still is a center of mass between the Earth and the Moon, even though the Earth and the Moon are not attached. So don't confuse that. Don't think that you can't have a center of mass because they're not attached. Now we can attach them. We can put them on a rod in order to make it a whole rigid system so they can't move relative to each other, and ask where the center of mass is. And often we will just say they're attached by a rigid massless rod so that we don't have to worry about the rod's mass, but we're just making it a rigid system so they can't move relative to each other. But maybe the rod itself has mass, in which case it's going to change the position of the center of mass. And that's the problem that we're going to do here. Okay, so let me undo everything we did there and start with my problem. Let's say I have a rod, which is at the top, and that rod is not massless. Let's call this rod mass m. And let's say that the rod has a mass m of 70 grams. And we need to say, in order to ask anything about its center mass, whether it is mass that is evenly distributed about the rod or unevenly distributed. Because if it's evenly distributed, we know that the center of mass of the rod is at the center of the rod. Okay, so we say it's evenly distributed so that the center of mass of the rod is at its center, right? So that's the center mass of the rod. Let's make the rod a length of 1 meter. Let's make it a meter stick. We can say that it's got a length of 1 meter. It's a meter stick. Let's treat these two masses, m1 and m2. We're going to add them to the rod. So we're going to treat these two masses as if they're point masses. We're not going to worry about their extent, or we can just say, hey, they're blocks, but their center of mass is at their center. So we are just going to make a rigid system. So let's say that m1 has a mass of 25 grams and m2 has a mass of 50 grams. And let's place them on the meter stick. Let's place m1. So now I'm going to move m1. Imagine I add it to the meter stick and I hang it from the meter stick. Let's just say I tie a string to the meter stick and I hang m1 right here. So this is, I'll just put 1. And let's say that its position along the meter stick, x1, is equal to 10 centimeters. Let's put it at the 10 centimeter mark. And let's take m2. And let's put m2, let's hang it, I don't know, we can hang it arbitrarily, but let's just hang it right from the end. m2, this is 2, block 2. That's meant to be block 2, a little hard to read. Let me try that again. Block 2. And let's put it at a position on the meter stick. x2 is at the 100 centimeter mark. Okay, those are the marks. So where does this system balance? Where does this system balance? What I'm asking is, where can I put a fulcrum, right? So put just a triangle, a razor edge, so that it balances. And the answer is not where I put it, right? Because there's more mass to the right than there's, well, actually that's a bad argument, but hopefully you can see it's not there. Hopefully you can sort of see that because there's because we've got the heavier mass to the right, then the center mass ought to be slightly closer to the heavier, at least closer to the heavier mass than the lighter mass. But anyway, let's see where it balances. Where along the meter stick does it balance? Okay. So how do we do that? Well, this really is, even though this is a three-dimensional problem, it's really a one-dimensional problem. Because we don't care about where it balances in the depth of the page, because everything's hanging down. I guess I had implied that, right, this is down, the gravitational acceleration is in that direction. We don't care where it balances in the vertical direction, because everything's just hanging. We just care where it balances in the horizontal direction. So it's a one-dimensional problem. X center of mass is equal to, there's three masses here, right? There's three masses, mass 1, M1, M2, and M. So X center of mass is M1, X1, plus M2, X2, plus M3, X3, over the total mass, M1 plus M2 plus M3. That's just the definition of center of mass. Now we've got to identify what M1, M2, and M3 are. Oops, I call them M1, M2, and M3, but actually the masses were M1, M2, and M. So I'm going to start with that, right? You might have questioned that when I wrote it down, and that would have been good. So I'm going to write that. I mean, you could have just said, oh, M3 is M. M3 is M. And the position of M3 is whatever the position of the meter stick is. But I'm just changing that to drop the subscripts for the things that indicate the meter stick. So now, how do we do this problem? Well, you might think it seems obvious, but let's just be very clear that the first thing you have to do is to define your x-axis. You got to define your x-axis. And the x-axis, because we are going to try to balance it at the meter stick, is going to be along the meter stick. That's my x-axis. I'll just draw it to the right. Doesn't really matter if it's to the right, to the left. It doesn't matter at all. Where do I put my x equals 0? Well, you can put your x equals 0 anywhere. You might say at the center, but then x1 is going to be at minus 40 centimeters, and x2 is going to be at plus 50 centimeters, right? Which is fine. But since we already gave x1 is 10 centimeters, that's actually measured from the left end. And x2 is 100 centimeters, that's measured from the left end. So I'm going to call the left end x equals 0. Define it anywhere you want. So that means that when I'm plugging into the center of mass formula, go back to purple, M1 is mass 1, 25 grams. Position of M1 is at 10 centimeters, plus 10 centimeters. I'm being careful. M2, mass M2, is 50 grams. I'm taking into account my units and my signs. And the position of M2 from the origin is plus 100 centimeters. You might say, wait a second, didn't I earlier say it would be easier to put my origin at one of the masses? And absolutely, it would have made my math a little easier if I had put the center of mass at the origin of one of the masses. Well, let's just do that later. I'm going to skip that for a second. Okay, let's keep with the one we got now. Plus the position of M, the meter stick. What's the position of the meter stick? Remember that for an extended mass, the position of the extended mass, if the mass is distributed equally, which we said it was, is at its geographic center. So it is at what position? 70 grams times 50 centimeters. That's the meter stick's center, 50 centimeters. And that's 50 centimeters from the origin. So let's go ahead, and then it's M1 plus M2 plus M3, 25 grams plus 50 grams plus 70 grams. Or M, I keep on calling it M3, doesn't matter. Okay, so another thing to recognize is you might say, do I have to change the units? Absolutely not. You do not have to change the units. Because if it's a center of mass, this is a position, the masses have to cancel. So as long as you use the same units for the mass everywhere, they have to cancel. As long as you use the same units everywhere. And then, whatever units you're using for distance is the units you're going to get for the center of mass. So if we can leave everything in centimeters, the position of the center of mass is going to be in centimeters. You do not have to change the units. So what do we get? So when you plug in those numbers, you get 60.34 centimeters. So it balances Remember that the center of this meter stick 50 centimeter mark was here. That's the 50 centimeter mark. So it balances at the 60.34 centimeter mark. It's about here. So it's going to balance here. We can put our balance block there, and the whole thing will balance on that knife edge, on that triangle. Really quickly, go back and change my origin. Let's say we were back here where we wrote down the equation for the center of mass, and we say, oh, we have to define our origin in order to know what x1, x2, and x are. Let's put the origin where one of the masses is. Rather than putting the origin where mass 1 is or mass 2 is, I'm going to put the origin at the center of the meter stick. So let's just call this x equals 0. If that's x equals 0, now you've got to be careful, but you should be able to figure this out, that m1, 25 grams, x1, the position, is relative to that origin. So if the center, if x equals 0 is at the meter stick's 50 centimeter mark, then x1 is no longer 10 centimeters. It's at minus 40 centimeters. It's 40 centimeters to the left of the origin. x2, m2 is, we have to put in the number, m2 is 50 grams. x2 is plus 50 centimeters. And m, the mass of the meter stick, is 70 grams. And the position is 0, because the position of the meter stick is at its center at 50 centimeters, which is where we put the origin. Still over m1 plus m2 plus m3. And what we get when we plug in the numbers, plug those numbers in, you've got to, remember we have a minus sign there, and what you end up getting is 10.34 centimeters. Say, ooh, that's a different number. And the answer is no, it's not a different number, right? It's 10.34 centimeters relative to the origin, which has been moved over 50 centimeters. So the balance point is still at the 60.34 centimeter mark on the meter stick, 10.34 centimeters to the right of our origin.